Hi, my name is Yuqi Wang, a PhD student from the Institute of Automation, Chinese Academy of Sciences. This is the presentation of our paper, Driving into the Future, Multiview Visual Forecasting and Planning with World Model for Autonomous Driving. The concept of world models has recently gained significant attention. Turing Award winner Yanla Kun advocates that learning world models, understanding how the world operates and evolves, is key to achieving general artificial intelligence. In his paper, he describes world models as critical modules that predict future states based on the current state and a sequence of actions. Essentially, a world model is a predictive system that simulates and understands the evolution of the physical world. The ability to forecast the future reflects an inherent understanding of the world, including its common sense and fundamental principles. The recent surge in interest around world models is largely due to OpenAI's Sora model, which has revitalized the concept by using video generation as a world simulator. Video generation for the physical world is akin to language modeling for the digital world. In autonomous driving, while end-to-end technology has made significant strides, it still lacks cognitive reasoning. Most research on world models has focused on text-to-video generation, with less emphasis on real-world interactions. Our work, Drive WM, bridges this gap by integrating these two areas. Drive WM is the first to implement a multi-view generative world model and combine it with end-to-end autonomous driving. Drive WM combines world models with end-to-end planning models, enhancing the safety and robustness of autonomous driving systems. Here's how it works. Drive WM enables the world model to predict multiple future scenarios based on actions provided by the end-to-end planning model. Then, using visual feedback from imagined scenarios, the end-to-end planning model selects the best decision. As illustrated below, Drive WM generates various future scenarios, like going straight or turning, based on the current scene. The world model imagines these scenarios, providing visual feedback on road conditions, traffic signals, and obstacles. The end-to-end planning model utilizes this feedback, along with current goals and constraints, to make optimal decisions. To achieve our goals, we encounter two major challenges. Firstly, we must construct a multi-view generative world model that ensures consistency across different perspectives and over time. Secondly, we need to figure out how to leverage this model to assist end-to-end planners. Current planners often struggle with degraded performance when faced with out-of-distribution cases, limiting their adaptability and applicability. By harnessing the generative capabilities of the world model, we aim to enhance planners' ability to handle diverse and challenging scenarios. To tackle the first challenge of building a multi-view video generator, we took a joint modeling approach. For the temporal aspect, we employed two-stage training to maximize the utilization of pre-trained image models, enabling our model to concentrate on learning temporal parameters. To maintain consistency across various views, we utilized a stitching technique. Essentially, we produced videos from three perspectives and seamlessly merged them using conditional information to produce a unified multi-view video. This approach ensures that our model generates videos with coherent and visually consistent content from multiple perspectives. We evaluate the visual quality of our multi-view videos from both quantitative and qualitative perspectives. Our model performed exceptionally well on both metrics, demonstrating its capability to produce high-quality videos. Additionally, we present examples of multi-view video generation using the NUScenes dataset. Our model also demonstrates excellent controllability. Firstly, our model can flexibly edit the overall scene. For example, by inputting specific text descriptions, we can control the weather conditions of the scene, transitioning from sunny to rainy, or from daytime to nighttime. We can also adjust the overall layout based on the bird's eye view layout. Our model can also control the positions of other agents in the scene, and the ego actions, such as moving forward and backward. Our world model also possesses the capability to generate rare events, such as making a U-turn in rainy weather or driving into bushes, which are relatively uncommon but crucial scenarios in real-world driving. The second challenge is using the generated world model to aid the end-to-end planner. It hinges on the world model's capacity to forecast future states from various trajectories. Our solution entails the planner suggesting multiple potential actions, while the world model imagines and creates corresponding future scenarios based on these actions. These scenarios offer valuable visual feedback to the planner, allowing it to assess different actions' visual rewards. As a result, the planner can make optimal decisions and choose the most suitable actions. We mainly explored using maps and bounding boxes as rewards to evaluate the model's imagined future scenarios. In the future, we plan to optimize the visual feedback mechanism by leveraging the comprehension capabilities of large models like GPT-4v to analyze complex scene elements more deeply. The world model significantly enhances driving safety by foreseeing potential risks through future scenario evaluation. This enables the planner to make safer decisions, markedly reducing collision risks. The world model significantly enhances the end-to-end planner's robustness. Traditional planners trained on expert-supervised data struggle with anomalies and out-of-distribution scenarios, leading to performance degradation. By generating diverse future scenarios, the world model provides richer training data, encompassing normal and abnormal situations. This broader exposure enables the planner to adapt and address potential risks effectively during training. Looking ahead, we're optimistic about enriching world models with larger and more diverse datasets. However, we recognize the current limitations of these models in simulating physical interactions. Our focus in future research will be on addressing these challenges. Thanks for your listening.